Hello everyone, and welcome to today's workshop on atmosphere monitoring for the Copernicus WEkEO service. So my name is Gaëlle Enarf-Sterbik, and I'm a training officer at Mercator Ocean International, and I'll be your host for today. So as you know, we will have a two-day workshop, and today we will have a more introductory session where we'll tell you about what the Copernicus WEkEO service is about, what sort of data and products you can find, and what sort of applications you can do with the data we provide to you. So before we start, we are going to go through some house rules and guidelines to help you follow these workshops in the best possible way. First, so you need to access the audio logo on your bottom left part of the screen to hear us, and then we ask you not to use the chat that you see on your right-hand side for your questions. So you can use it for small talk, say hello to us, discuss with each other. But if you have a more technical question, we will use the Q&A session on the website. Okay, so my internet is a bit slow, sorry. Okay, yeah. So you will see there is a section dedicated to the Q&A on the website. We will also put the link on the chat, so no worry. And yeah, so you can ask the question for the speaker here for today, and that's why we will answer them. You will also find a survey next to it that you can answer at any time. So as usual, if you can take 2 minutes of your time to answer this, it would be very nice. Okay. And yeah, so today the agenda, so I will be the moderator and giving a quick introduction to WEkEO. And then we will have 5 presentations. The first one will be done by Chris Stewart from the European Center for Medium Range Weather Forecast. So he will give us a presentation of the Copernicus Atmosphere Monitoring Service. After that, Peter Albert from EUMETSAT will present to us a WEkEO tool called EOCanvas for cloud-based data processing. And then after a short break, we will have 3 presentations about specific applications of these Copernicus projects. So we will have Augustin Colette from the French Institute on Industrial Environment and Risks. Then we will have André Brodtkorb from Oslo Metropolitan University. And finally, we will have Konstantinos Politakos from the Remote Sensing Lab of FORTH in Greece. So it promises to be a very interesting morning, and I hope you enjoy it. So I'm going to go first with the small introduction of the Copernicus WEkEO service. So what is the Copernicus WEkEO service? So WEkEO is a data and information access service. So it is a program funded by the European Union, and it was basically created to facilitate the access to Copernicus and Sentinel environmental data in the WEkEO platform. What we offer in WEkEO, as I said, and as you can see, so it's an easier access to environmental data, but also cloud infrastructure and very competent user support to help you if you have any question. WEkEO is operated by the different entities that are entitled to manage the different Copernicus services. So if you haven't heard of Copernicus, it's a European Union's program dedicated to Earth observation and to monitor the Earth. So we have different entities that are responsible for the different services. We have Mercator Ocean, ECMWF, EUMETSAT, and the European Environment Agency. And the Copernicus services are the following: the Copernicus Land, Copernicus Marine, Copernicus Emergency Monitoring Service, the Copernicus Atmosphere Monitoring Service, and beside that, we also have Sentinel missions, which are the satellites that provide the data that you can find in Copernicus, and they also have some missions which data you can also find in WEkEO. And all of the data are free of charge to access and download. You just need to have an account. So now that you know about the different services and what they offer, how can you access WEkEO? So you access WEkEO through its website, and you will be able to find the catalog with the products, and you will find more information on computing resources. You can find use cases, you can access the events that we organize, and many other materials. And also, the 3 main points of WEkEO and why it is an advantage is that it provides direct access to Copernicus service data, which is directly linked to the original sources. So the data you download are not a copy, it's the original of the data. So it's the access is harmonized, so it facilitates some programming and analysis that you might need to do with the data. And as I said before, you have very active user support that's here to which are here to help you. So as for any Copernicus delivered data, the access to WEkEO is free and the access to download the data is also free. So it's an open source data, environmental data. And you can also access e-learning materials for free also, like for example, Jupyter Notebook. And if you have more experience, for example, or if you would like to have some computing power, that's a part where we apply a cost to it, but for the rest, to visualize and access the data, it's free and open to everyone. You can also have access to a Jupyter Lab. So if you have heard of Jupyter Notebooks, it is a nice way for you to learn how to use the data, how to do basic analysis and kind of track your evolution, because we share it through the Jupyter environment and you can learn a lot through this platform. So for that, you can also access our Jupyter Notebook gallery, where you will find a lot of notebooks already developed on different services. You will also have access to virtual machines. I will not go into that today, but don't hesitate if you have any question related to this. Yeah, so very useful for more of a computer power. And yeah, finally, I spoke about the user support. So as you can see, if you have any question, it's very easy to contact the user support. You can either do it by email through the help center that you will find on the website. So it's quite easy and don't hesitate to do so. And yeah, that's it for me for today for the introduction. So I hope you got a little glimpse of what WEkEO is about. And now we will dive a little bit more into the product itself. And so, yeah, we will now go to the Copernicus Atmosphere Monitoring Service presentation. And yeah, I'm inviting Chris. Hi, Chris.
Hello. Good morning.
Hi. So yeah, you can start your presentation.
Thanks a lot. Yeah, so my name is Chris Stewart, and I work at the European Centre for Medium Range Weather Forecasts. And I'm going to give you a presentation now on the CAMS, the Copernicus Atmosphere Monitoring Service, and the tools that it provides. So what I'm going to do first is just to share my screen. So first I need to put this into presentation mode. Then So can you see my screen in presentation mode?
It's in the right mode.
Okay, perfect. So yes, my presentation will be about the products available through WEkEO from the Copernicus Atmosphere Monitoring Service. So you've already had an introduction from Gail on Copernicus, so the European Union's Earth Observation Programme, which includes a fleet of satellite constellations for monitoring the Earth system, but also there's a service component where we take this data and provide value-added services across different sectors. So ECMWF is entrusted with two of these services, the Copernicus Climate Change Service and the Copernicus Atmosphere Monitoring Service. And we also provide support to the Copernicus Emergency Management Service. And what we do is we provide open and free information products based on the satellite data and also in situ data. And this data includes, so the products we provide include past, current, and near future forecasts of global atmospheric composition and also reanalysis. We also provide information on the ozone layer, so stratospheric ozone as well as tropospheric ozone. We provide European air quality data, emissions and surface fluxes of key pollutants and greenhouse gases, also solar radiation time series, and global radiative forcing. So in the slide here, you see some example products from CAMS, and these are all available through WEkEO. And the way it operates is we take the data, and then we assimilate the data into our global model. So we have at ESMWF the integrated forecasting system, but we also have for regional air quality, European air quality, we manage a series of systems, different independent systems, and we provide the data from these as well. And on the right-hand side, you see some example products, some example forecasts from aerosol optical depth. And just to mention that we do have some direct users. So we have many people are taking this global and regional data and using it directly, but we provide, we have a specific role in the kind of data value chain. And what we do is we support downstream services to do further value adding on these products. So let's say, for example, you have an entity who wants to deliver a service using very high resolution data. So they want to provide high resolution information on air quality at the kind of municipal scale. Then what they can do is they can take the global data and they can do some downscaling, and then they provide a service to their own users. So basically, we purposefully do not provide super high resolution information products because there are other entities who can do that. So basically, we have people who are using our data directly, but we also have a lot of indirect users who are using value-added products from these other services. So there are entities, small companies developing, for example, mobile apps. We also provide our data to different channels such as Google, news channels. So the data is very much visible and it's used, and it's also been disseminated to a very large number of users. And this slide here just shows the complexity of the process in terms of taking the satellite data, assimilating it into the models, and you see the difference. So in this very complex table here, on the left-hand side, you see the satellite instrument. And then you've got the sensor, sorry, the satellite platform, the sensor, and then you have the different species that it monitors. And we take the satellite data and we assimilate it into the CLAMS global system. It's only satellite data used. We use the in-situ data for verification and assimilation into the regional systems. And then, of course, what you don't see here is all the data that's used for the ESMWF numerical weather prediction assimilation system, which is a huge quantity of data. So here we're just talking about atmospheric composition. And this slide just shows you the added value of new missions that come along. So, for example, this shows the reduction in the relative carbon monoxide bias, having assimilated tropomi data into our system. So you just see here, for example, a series of charts where, especially in the kind of troposphere, you see a greatly reduced bias in CO after having assimilated tropomi data. So we're constantly improving the system. When new instruments come along, and new data comes along, and we're improving the products for our end users. So the main purpose of this presentation is just to give you a flavor of the different information products that we provide. So, for example, we have forecast products and forecast products of very many different variables in atmospheric composition. This is an example of CAM's total aerosol optical depth. So, we provide forecasts for the global data 5 days ahead, every hour, 5 days ahead. But what you're seeing here is an animation of the analysis. So basically, it's taking the observations, assimilating them, and providing the best estimate of the current state. And this is done for multiple time steps. And then what you see in the charts are a comparison of the forecast data with data from RSLab, from this network of ground-based remote sensing data. So that was total aerosol optical depth. And here's an example of SO2 from volcanic eruption, the Cumbre Vieja volcanic eruption on La Palma. And again, you see the comparison with AeroNet. And so in addition to the forecast, we also have reanalysis. So basically, we're taking all of the analysis time steps for past decades, and now we have over 20 years of reanalysis. So basically, reanalysis is filling in the gaps in space and time. So you have a consistent data set going back multiple decades, where you can really look at past trends that will give you an indication of what the future may be like as well. So we have this reanalysis data, and there are different things you can do with this. So this is one example. You can really put events into context. So what you're seeing here on the top left, you see the climatology for January. So every January from 2003 to 2019 in this case. And on the top right hand side, you see the climatology for June. Okay, for every June for that whole period, and you see the average there. And then on the bottom, you see the anomaly with respect to that climatology for a particular year. So in this case, it's January 2020. And you see that there is January and June. So you see that, for example, there's a big dust event, which is much greater than the average. So that's actually the Godzilla dust event. But for the wildfire emissions, you actually see a lower than average emissions. Okay, so this is an interesting data set to put these kind of events into context, to see actually how significant was a particular event. So in addition to the forecast and analysis, the forecast and reanalysis data for atmospheric composition, we also have global wildfire emissions. So this is an animation here of fire radiative power. So this is taken from the satellite data. In addition to that, we also have various different emission products. So anthropogenic emissions for different sectors. We have shipping emissions, biogenic emissions, and this is all available through WEkEO. And just an example of what you can see with this data. So in 2023, that was actually a record year for Canadian wildfires. And you can really see how significant it was that year. So if you look at the chart on the top right, you see total wildfire emissions over the kind of wildfire season. And you can see that compared to previous years in the gray dotted lines. And then you also see in black the 2003 to 2022 mean. So you see just how significant it was, how many more wildfires there were, how much more emissions resulted from them. In 2023, it was really much greater than previous years, also greater than last year, even though last year was also pretty intense. So this This slide just shows a comparison between the fire radiative power in Africa with also the carbon monoxide volume mixing ratio. So basically you see the emissions, you see the fire radiative power, and then you see also the emissions in two separate figures. So you can make a comparison with these, and you can also look at the time series. So in addition, so we've spoken about the forecast, reanalysis, emissions, also greenhouse gas information products. So we have, which are also available in the emissions data and in the forecast data and reanalysis. But this just shows you what kind of visualizations you can produce with this data. So we have animations, daily global forecast of atmospheric CO2 and methane, at high resolution. And by the way, this is available at different levels of the atmosphere. It's not just 2D, static data. And we also have the greenhouse gas information in the form of activity-based emissions and flux inversions. Also, we have products on the ozone hole, so stratospheric ozone. And if you look at some of these figures, these are actually available on the CAMS website. So you can recreate these using data from WEkEO, but if you don't want to process all of this data, you can also just go onto the CAMS website, and you can monitor the state of the ozone hole through these various charts, and you can see how significant it was in any given year compared to previous years. So, and there are several animations and lots of information from the website on this. And it's not just the actual ozone hole itself. So CAMS now monitors also the chlorine radicals that break down the ozone. So that's the middle figure there. And also the so-called reservoir species that bring chlorine to the region. So that's on the right-hand side. So it's not just the ozone itself. And then finally, climate forcings. So this is also something that's available through CAMS. So this figure here just shows, you've got the methane and the ozone slightly positive. That's kind of offset by the negative aerosol climate forcings. But of course, the main driver is the carbon dioxide, which is still increasing, which is quite high and still increasing. And that really is what drives the global climate forcings. So again, you can get this data, you can analyze it, and it's all freely available through WEkEO. So that was just a very quick overview of the different data products. I'm just going to mention, given that this is a training webinar, I just want to mention also some of the learning resources that we have. So we have a lot of, so Gail mentioned the Jupyter notebooks. We've got lots of Jupyter notebooks on that show how to handle this data, how to access, process, and visualize, and do different things like unit conversion and various different calculating the size of the ozone hole and all these kind of things. So they're basically workflows in Python that provide good tutorials on best practices for handling this data. We also have a lot of material from past trainings. There are some massive open online courses, and the material is still available for those. So I really recommend delving into some of this material. And here just some links to different learning resources. And I think that's pretty much the end of my presentation. So I think now there's a bit of time for questions. So I'll stop sharing my screen.
Thanks a lot, Chris, for your presentation. So it was a really nice presentation about the service, and we are going to go through the different questions we have for you. Okay, so the first question, which programming language are you using for the data modeling system? Is it Python or a different language? What about for satellite data assimilation?
Okay, so I think they're using Fortran still a lot, but I'm not sure. So this is for the actual operational modeling system, right? Yeah, I mean, I think they're using various different programming languages. I don't know exactly. I think they're still using Fortran a lot. What about for satellite data simulation? Yeah. So, I mean, I'm not involved in the operational data simulation, but yeah, I think they're using different programming languages. If you use data for a third-party app, I assume you pay to use the data. Right. So the data, all the data that we provide is, or all the data products that we provide are free. And this data can be used for third-party apps. So basically, even commercial businesses can use our data for free, and they can develop a business around that. So our data is always free. But maybe the question is, if you use data from a third-party app, I don't know. I assume you pay to use the data. So yeah, I don't know how the costing model works in terms of taking using, well, the satellite data is from Copernicus is free, so there's no cost associated with that. And in terms of other data, I think there are different agreements in place, but I think the key thing is that the data that we provide is completely free. Then how can I download all CAMS data variables? Can I download all CAMS data variables, models, etc. available in the ADS by WEkEO? Yes, you can. So I think now that there were some issues before, but I think now everything is available. So I think they're quite well synced now. Everything's on the Atmosphere data store is now also available through WEkEO. How precise, accurate, and meaningful are the results of CAMS analysis in measuring the air quality index? Right. Okay. So we do evaluate. So that there's validation and evaluation of our data. I think I'm not the one to say how good that is compared to maybe other systems. But unfortunately, Mark, my colleague, is not here today. He would normally be presenting in this presentation. But I can try and find out more concrete data if that's needed. Otherwise, if you go to the CAMS website, you can find very good information there. So yeah, there you can get good information on the data quality. I think it's pretty good. Derived from all your different surveys, do you have data on land cover and land use as an available product? So I think that's more the Copernicus land service that provides this kind of data. So yeah, it's best to get that from there.
Some of them are on WEkEO, but I think there is also more on the Copernicus land monitoring service also.
Yeah.
Okay.
Given the availability of 2D greenhouse gas data, have you ever used 3D modeling for greenhouse gas modeling as well? Okay, so when you say 3D modeling, I mean, it's already, I mean, it's even 4-dimensional. So we've got, you've got latitude and longitude, you've got different layers of the atmosphere, and you've also got the time dimension. So in that sense, it's 4-dimensional. So I'm not entirely sure what this question, given the availability of 2D greenhouse gas data, have you ever used 3D modeling? I mean, basically, we're doing 4-dimensional modeling. So yeah. Unless this person who's asking this question maybe wants to elaborate further. I'm not sure.
I will keep the question on the side just in case.
Yeah.
But yeah. Oh, okay.
Is it possible? Is it possible to download data as CSV or Excel for one or more parameters in a time series format, hourly data? Okay. So for some data, I mean, most of the data set is in grid format, which is a particular kind of WMO defined meteorological data format. Or NetCDF. So we also convert that data to NetCDF. But basically the original data comes in grid format. But we do have Jupyter notebooks that show how to read that data and how to read it into a Python object and process it further, and even export it into a different format such as CSV. I don't think in CAMS, but for some of our data, for example, in C3S, when we produce the European State of the Climate, we make available the data that goes into these reports, and that's available in CSV format. But it's only a very few cases where we have the data in CSV format. In the vast majority of cases, it's in GRIB or NetCDF. But again, there are tutorials that show you how you can handle that data.
Thanks.
How involved are government agencies in the development of products for regional local cases? Okay, so we do have what's called a national collaboration program. So this is a program which involves national entities from the different countries who who develop further services based on our products, and we have an active collaboration with different national entities. So in that sense, many of them are government agencies, and they're very much involved, very much in collaboration with CAMS. So yes, we are very much involved with government agencies in the development of products for regional local cases. And you can get all the information on that from the website and from the service elements such as the NCP. I use ERA 5. Is this now available through WEkEO? Yes, ERA 5 is available through WEkEO. So ERA 5 is actually developed through the Copernicus Climate Change Service, but that's also available through WEkEO. So all of the C3S, the Copernicus Climate Change Service and the Copernicus Atmosphere Monitoring Service data is available through WEkEO. Can CAMS forecasts be accessible through WEkEO services or other OGC protocols? Okay. So I think so. I think so. I know you can get so on already on places like Google Earth Engine, you can find ERA 5 data, for example, and so yeah, I think some of this data is available, maybe not all of it. Chris, you mentioned reanalysis of forecast products. Which CAMS product would you recommend for current meteorological data, past 7 days to now? Okay, so it depends so if we're talking about numerical weather prediction data, it's best to look at what ECMWF provides. So ECMWF provides meteorological data up to 10 days, up to 10 days, but also sub-seasonal to seasonal, decadal, and many different timescales. But if you're interested in past 7 days and meteorology, then it's best you go through the ECMWF kind of core meteorological data offering, many of which is now open. So in the past, there was, and there still is to some extent until the end of this year, a license applied to the use of that data. At the end of by the end of this year, it'll all be under an open license. So that's all accessible. However, through CAMS, many of the variables are also meteorological variables, but what CAMS focuses on is the atmospheric composition. So it's not so much the meteorology; it's more the the atmospheric trace gases and aerosols, very much the composition of the atmosphere. So for climate projection, are you using CMIP6 multi-model, or which model are you using? So yeah, so that's more for the Copernicus Climate Change Service. And yes, we make available CMIP6 data, and we're using CMIP6 data also for the different kind of sectoral application data sets. But we're also using CMIP5 as well as CMIP6. So that is available and that is being used. Is fire data available in real time through WEkEO? Okay, so what we provide through the ADS is also synced with WEkEO. So yes, it's also available through WEkEO. So the fire radiative power and fire emissions data, that's available through there. What kind of use cases do you see for CAMS data most relevant for being used in the management of renewable energy production? Okay, so what kind of use cases do you see? Okay, so CAMS data is very relevant also for renewable energy. For example, the solar radiation time series is very good for kind of photovoltaic plant management and for solar energy products, but also lots of other examples. I mean, I can't list all of them right now, but there are many data sets that are definitely extremely relevant to renewable energy. And if you go onto the CAMS website, you'll also see examples of use cases. So I would suggest going there, as well as exploring the actual data that's available through WEkEO and through CAMS. I hope I managed to answer those questions.
Thanks a lot, Chris. So we don't have time to do all of the questions, but all of the remaining questions will be put on the site to be answered later, no worries. We will also provide some useful link in the chat again concerning the website. And yeah, the slides will be made available during the day, so no worries for the question asking about that. Yeah, Chris, thanks again for your nice presentation of the service. I think everyone enjoyed it. And yeah, thanks again.
Great, thanks a lot. Thank you.
And yeah, so now we will go to the presentation of the WEkEO tool EOCanvas. So Peter, welcome.
Good morning, thank you.
Hi.
I'm also going to share my presentation. Do you see it?
Yeah, perfect. Thanks.
Thank you. So good morning, everybody. My name is Peter Albert. I'm with EUMETSAT in the Copernicus program. And in the WEkEO context, EUMETSAT has two roles. On the one hand side, we are part of the Copernicus space segment. So we provide Sentinel satellite data for marine and atmosphere observations. And we are providing the technical infrastructure for the WEkEO platform. And in that context, I'm presenting you today a new service called EOCanvas, which can be used to process Copernicus data on the cloud. Now, what is EOCanvas? It is a new service. It's a framework with which users can process the WEkEO data on the cloud. And more specifically, the EOCanvas itself is a Python library to help users to work with the more general API. The EOCanvas is embedded into the overall set of tools we offer in WEkEO. So feel free to go to the new web portal, which has been launched in January, and which gives you a nice overview over all the available tools, starting from viewing the data, discovering the data, then working with the data in a workspace, which comprises a Jupyter Hub. And then just to give you the context, the EOCanvas is on the advanced tools. So it's not something you can just play around with easily. It's an advanced tool which needs some preparation and some knowledge about the data and about the available capabilities. But then it's very flexible and gives you a lot of flexibilities. And I'll show you one example later in this presentation. So why should you use the EOCanvas? The classic way of working with Earth observation data is typically you download the data to your local machine and you do then the local processing. In the current days, this comes more and more with the growing disadvantage that it really requires a large bandwidth and a large local storage and computational resources, because the data volumes of the satellite observations grow and grow. So it's becoming more and more difficult to process all of the data locally on your system. And that's why pre-processing in the cloud, ideally close to the data, comes to play, because it can significantly reduce the local resource requirement you need for processing the data, because you only have to transfer the results of the processing to your local machine. So EOCanvas is a framework. So it's a set of tools which allows different applications to be run on the data available in WEkEO. And we have currently implemented the ESA Snap toolbox and the UMITSA data tailor. So you can work with the satellite data at the moment, but the tool is flexible and can be enhanced. So if the user community, so you have requirements, recommendations for additional tools you would like to see implemented, then feel free to contact us and we can consider additional tools for implementation and making them available to the public. The workflow of the EOCanvas as follows. So as a user, you first specify your data search request, in which you typically specify the area of interest and the time of which you need the data. This search request is then sent to the WEkEO Harmonized Data Access for data retrieval, but the data is not downloaded to your local system, but stays in the cloud where it's then processed. As a third step, you specify then the workflow specification. So you tell the system which type of processes you want to run on the data. The data is processed on the WEkEO cloud infrastructure, and then you only have to download the results. And it was already mentioned. So the harmonized data access in WEkEO has the advantage that it's always providing the original data from the respective source. So when you're accessing CAMS data or Sentinel data through the WEkEO Harmonized Data Access, you can be sure you get the proper authoritative Copernicus data provided by the original source. And word of warning here, so the workflow specification, that is the critical part, because that is tool dependent and needs some familiarization with the tool. So that is admittedly an initial obstacle, but it provides a lot of flexibility and processing power, because I don't know if you are familiar, for example, with the Snap toolbox, you can set up complex Snap workflows consisting of several processing steps, and those workflows can then be sent to the EOCanvas for very personalized processing of the data you want to achieve. And I will now go to an example. I will use the 2024 Portugal wildfires to show you a little example of the processing. Oh, and that was too fast, so I stop sharing here. And I will now share a Jupyter notebook. Where is it? Just a second. Here it is. Can I select this? Yeah, no, wildfires share. Okay, can you see the notebook?
Yes, we can.
Okay. So, well, it's a simple use case. I only want to show you how to create images from a wildfire event using Olchi images. And in the notebook, we will reproject and resample Olchi level 1 data using the EOCanvas, work with multiple inputs, and then visualize the results. And the background is that the Olchi data, if you download the granules, they're really large. So if you have to work with many granules, you have to download large volumes of data. And through the usage of the EOCanvas, we do the subsetting and resampling in the cloud, so you only have to download smaller files. As typical with Python, you import a lot of modules to be able to work then with the tools. We are specifying here the area of interest, so it's an area in Portugal, and we know that the wildfires occurred in September 24, so I'm having a start date from 16th to 20th of September 24, specifying a download directory. And I should note that I'm not running the notebook in real time here because it takes all in all something like 10 minutes, so it would be slightly too slow for showing it online, but I ran it this morning. This here is the search query for retrieving the data with the HDA. And you can actually, so it specifies the dataset ID using the start date and the end date and the bounding box, and yeah, how many items you want to download or search. And you don't have to do that from scratch. If you are using the WEkEO viewer, you can actually use the catalog to find the product and then define area of interest and start and end date. And then through the WEkEO viewer, you can actually get this query JSON string to which you can use then in a notebook like that. Then the usage of the harmonized data access is easy. So you define your client, and this command here performs the actual search. And then with this command, I'm getting the download URLs. So as I said, the WEkEO harmonized data access provides the data from the original source. So those URLs are then pointing to the respective URLs, in this case, at the UMETSAT data store. But at this point in time, the data is not downloaded. It's really just the pointer to where the files can be accessed. And then now here comes the magic. So I'm using, for the data tailor, I have to specify a YAML file for configuration. And this YAML file I can open here. So that one is in structure really easy. So you specify the product ID. I need several bands from the OLG level 1 data, and I want geographic projection with a certain resampling resolution, and the output format shall be netcdf. And so that is a generic file which could work anywhere on the globe. So, and for the specific example here, I'm reading first the YAML file, and then I'm specifying the region of interest where I'm using the area of interest I've specified above, which covers Portugal. Now, in this notebook, I'll also show another thing with so running the EOCanvas in parallel. So it's not just a simple hello world where you just run one call to the EOCanvas, multiple, so it's slightly more complex. And so I'm using the thread pool executor here, and this function is sent to the executor for processing, but this is the command which actually runs the EOCanvas. So you are calling the data tailor process. I'm specifying the processing chain I've specified above, and the input is a variable here, which is specifying mostly containing the URL of the download file, which is provided to the function. And then here I'm actually executing then in parallel the calls. So I'm submitting here the function to the EOCanvas. For the files, the list of files which I've created in the search request above. Now I'm going down through a large number of log messages because, yeah, well, the job has started, and then it's running, and then it's finishing, it's downloading the data, and then I can show you that also here. So the downloads I've then retrieved are much smaller, so it's 30 megabytes per granule only, because it's only the subset over Portugal. And then in this simple example, I just want to post-process the data, creating an RGB image. So I'm having here a little function which takes different channels, weighs them, and maximizes them. So I'm getting a nice figure, and I'm creating here then an RGB image of the files, and I'm storing them as a PNG file then in an images directory. So I have the images, and as a last step, so some warnings, one of the file seems to have a problem. And then I'm creating here an overview of the files, and that is then the result. So you see here the 1, 2, 3, 10 images which have been created. You can see here the wildfires and the plumes which are created by the wildfires. And that's it. So that gives you a short overview on how you can use the EOCanvas to put some of the pre-processing of the data into the cloud, so you have to work with smaller files only. And then I'm going back to the presentation. A few remaining, and now this one has also disappeared. But it's now here. Okay. Yeah, so that was the demo. What are we planning for the future? So we are currently installing more software packages. Currently, it's the Thomas toolkit, which is a marine tool for creating collocations between in situ measurements and ocean color measurements from Sentinel-3. But as I said, we are open for suggestions from the user community. So if you have an idea for generic tools you think are relevant for the user community, you can contact the WEkEO user support or me directly to give recommendations. And if you want to start using the tool, there is several resources available. So through the WEkEO web portal, you can go to the Jupyter catalog, which has a lot of notebooks, not only for EOCanvas, but for all software tools, which we offer through WEkEO. If you filter for EOCanvas, you find several notebooks which cover additional features, also notebooks showing the usage of Snap. There are other notebooks which show how you can use the EOCanvas, not with the HDA, but with the S3 buckets for input and output of data. So there's a lot of material there. All the notebooks are also available on GitHub. So if you are on the WEkEO Jupyter Hub, you can find in the public directory under WEkEO for Data, WEkEO EOCanvas, you find the notebooks directly there and can take it from there and modify them and run them on the Jupyter Notebook. For the Python package, there is documentation available. There's a read the docs, which you can also get from the WEkEO portal. From the scaling up data access part, you click on learn more, scroll down, and then you come to that part, and then you can go to the read the docs. Also, so I can only recommend you to give it a try, and please give us feedback. And if you want to learn more about the WEkEO tools and services, including EOCanvas, but not only, then there is a series of webinars already planned in May. So feel free to watch the events section on the WEkEO web portal to get information and be able to register to those webinars when they come. And yeah, and as I said, so if you have questions on, and if you need more quota, that's also one of the things. So there's no such thing as a free lunch. The processing on the cloud is not unlimited, so user quotas apply. But if you have an interesting use case and you need more resources, you can also feel free to contact us, and then we can see and agree whether we can give you temporarily more quota so you can run your use case on WEkEO. And that brings me to the end of my presentation. Thank you.
Thanks a lot, Peter, for your nice presentation. So always a nice way to show some tools of WEkEO. So we will go to the question. So the first question, which other potential extensions for satellite images, aside from OCLI, can image in JPEG or PNG format be analyzed using Jupyter Notebook or EOCanvas?
Well, I'm not totally sure I understand the question correctly, because the satellite, I'm not analyzing the satellite images. So basically, talking about satellite data, you can work with all of the Copernicus Sentinel satellite data through WEkEO, through the EOCanvas. So you can work with the ESA Sentinel-2 data, Sentinel-1 and Sentinel-2 data through Snap. You can work with the AllShare or SLSTR data through the data tailor. You could create, of course, PNG or JPEG or TIFF or whatever format you want to create, whatever Python allows. So there's no limitation. And so you can use all the available Sentinel data. You can create images, but I would not say you can analyze the images, because the images is the end result of the processing.
Thanks a lot. So we will go to the next question.
I must admit that I'm not an expert on the ESA Sentinel data, so I can only say if the INSAR process is something which is part of the Snap package, then yes. I also know that there are some extensions to the Snap package which are also included. If it's totally different processing, then no. But then please reach out, and then we could see if we can make that available. The Sentinel-1 SLC data, also again, I'm not an expert here, but all the ESA-provided Sentinel data, which is available through the CDSE, is available through WEkEO as well. So the catalog should provide the data. If it's available on the CDSE, it's also available on WEkEO.
Okay. I can put the question on the side just in case also. Okay. Okay. So, is EOCanvas for free for all users?
Yes, it is free for all users with the limitation of the quotas. So resources are not endless.
Okay, thanks a lot. This question. So yes, on the GitHub, I guess it's available.
Not yet, because I worked on it last night and this very morning, but we'll make it available.
Okay. So we'll have to be updated on the GitHub. Oh, okay. Two of the same question, kind of. Would it make sense to connect EOCanvas to other data portals like the European Digital Twin Ocean, and same question for European Marine Observation and Data Network? So
That's a very good question. And I think I see two possible ways for the future to combine this, because EOCanvas is not a unique idea. So on the CDSE, for example, you have the OpenEO processing environment, and OpenEO provides an OpenEO aggregator, which makes it easy to combine remote cloud-based processing from different sources under one shell. And I think it would definitely make sense, and we are looking into that, to make the EOCanvas also work seamlessly together with other processing. So if the digital twin of the ocean would have a similar framework for processing data, then users could combine the different processing environments. If we want to use the EOCanvas processing and the WEkEO processing resources to use the digital twin output, then we would first have to make a link to the harmonized data access, so to have the Editu data available in WEkEO, and then install the respective tools to allow that processing. I think both are definitely interesting ways forward, which we will look into. And the good thing is that because Mercator is part of the consortium in WEkEO, we have it's easy to have that discussion, and we'll definitely discuss that further.
Excellent. Okay. And I guess it's the same answer for EMODNet.
Yes, but if I'm not wrong, that's mostly in situ data, I think. And in situ data is difficult because it comes on an irregular grid. And so the WEkEO, the harmonized data access, what we're currently having is mostly satellite data and level 3 data from the monitoring services, and so it makes sense, but I can't promise immediately that it will be available and easy to use tomorrow. But it's definitely something which makes sense.
Excellent. We have time for a question.
Yes, of course. It's just really, it was my limitations, because Snap, in order to make a Snap example, you first have to have Snap also locally installed to create a meaningful graph. So to have the graph is the term for I think for the Snap workflow, and I didn't have the time and resources, honestly, to prepare that. So I also thought it would be nice. Also, the time is limited, but it's definitely something for the webinar in May. I think we will have more time then, because there will be a session completely dedicated to, I think, EOCanvas and I think the EarthKit. And then we will have more examples also including Snap and showing the complete workflow.
Perfect. Yeah. So you will receive an email about this webinar in May. So no worries for missing the information. You will be aware of it. Okay. Is EOCanvas examples of Jupyter Notebook available also for air quality, aerosol data, and climate data? So we will also put the link to the Jupyter catalog on the chat for you to take a look.
Yeah, but I think the current examples are all on ocean examples, the existing examples on the Jupyter catalog. That's why I had to work myself on an, and I'm not an atmosphere expert, on an atmosphere example, but we'll talk to our experts and also see if we can provide more atmosphere related aerosol and other data examples.
Okay, thanks a lot. It's still okay. Okay, so last two questions. Is it possible to conduct all analysis with satellite imagery in EOCanvas, or are there limitations?
Well, currently there are of course limitations because, well, you can, in EOCanvas, you can do whatever Snap allows you to do or what the data tail allows you to do. So that is a lot, but there's of course limitations. So you can't do anything. Leaning myself out of the window now, but we have the plan to also an idea on how to provide the capabilities for user-defined code so that users can define the code they want to execute on the data, but that is just a plan. So I can't give you a schedule for when this will be available, but it's definitely a user need which we have identified and which we want to work on.
Okay, thanks a lot. And we will go to the last question. How can we access the WEkEO product? And is it possible that EOCanvas save in TIFF files beside JPEG or PNG?
So, well, I'm starting with the second part. So the EOCanvas output first is the core EOCanvas is what is provided by the tools. So I know that the data tailor, for example, could also directly generate quick looks. So you could download them. I have to check what the data formats are there. I guess it would, maybe TIFF is also available. And similar to the question we had already, because in my example, I did the image creation myself in Python based on the netcdf files I've retrieved from EOCanvas. And there you're only limited to whatever Python allows you to do. And then creating a TIFF file, I guess, is easy. I haven't done that, but I would expect no problems there. The more general question, how to access the WEkEO products. Well, the easiest way to start with is to go to the light viewer. Maybe if I have just 3 more minutes, then if it's the last question, I can quickly show the light viewer if you want.
Yeah, you can. Yeah. We will also put the link on the chat for people.
Yeah. But yeah, okay. Then let me just quickly, I'll share. And again, so I first need this window here. And then wildfire share. Do you see my screen?
Yeah.
So really WEkEO products. So if you go to the WEkEO website and then you can click here, start exploring for free. And that brings you to the new light data viewer, which has been made available only recently. And it's the easiest way to start discovering the WEkEO data. It's a subset, a selected set of variables to make it on purposefully easy to use. So if I'm going, for example, to the atmosphere data, but yes, it's working now. There was a problem, but it's back now. That's good. So you can show the ozone layer. You can show dust aerosol, particulate matter, nitrogen dioxide, and you can go through there's a timeline at the bottom, and you can visualize the data. So that's some of the, I think this is ERA 5 hourly data, and some of the variables you can visualize directly for a subset. If you want to go a step further, you can go to the expert viewer, which gives you access to all the WEkEO data. So because it has the embedded catalog, if you click on the plus here, you go to the WEkEO catalog, and then you can filter for the here for the services. So you can see for the C3S comes emergency land and marine data, and then for, let's go again here, for example, to the atmosphere data, you see all the data sets which are provided from COMS and air quality forecasts. You can select mass concentration of dust, you add it to the map, and then this is a European data set. And then again, you can visualize it here. And finally, if you're, now I have to log in now, because now when you want to start downloading, working with the data, then you need a WEkEO user account. And I hope I remember my password. Yes. And I will go back to the viewer. And then you click on this little button here, and then you select the variable birch pollen and so forth. You can select all the criteria. You can select an area of interest and put that here into the map. And finally, also now that gives me the possibility to show you what I said in the beginning. If you click on show API request, then here you get this JSON string, which you would use in the harmonized data access or in EOCanvas. Side remark, here, this data set you could not work with in EOCanvas because we are not supporting this data yet here. We have no tools which with which you can work with this data, but you could work with the harmonized data access. You can now request this data. Okay, I have to select more analysis. Let's just
Either way, on Wednesday we have the full demonstration of the.
Okay, then I'll stop here. So you could download the data in the browser, or you can use the API request to work interactively with the harmonized data access. And then I'm stopping here.
Well, thanks a lot for the presentation to both Chris and Peter. Yes, so for the rest of the WEkEO viewer demo, you have to come back in 2 days to have the full demonstration by the WEkEO user support. And yes, so now we are going to take a small break, so feel free to go grab a coffee, look at the polls or discuss with each other, and we will be back in a few minutes. See you! Welcome back, everyone. So I hope you had some time to take a little break, and we will go to the next part of our workshop. So we will start the use case presentation, and welcome, Augustin. So Augustin will do the first use case, and yeah, welcome, and thanks for joining us, and you can start whenever you want.
Thank you, Gail. Hello, everyone. I will be happy to present you a short overview of what can be achieved using the Copernicus Atmosphere Monitoring Service in relation to air quality policy support. So, yes. So my name is Augustin Colette. I work for a French institute working on industrial risks and environment. I'm head of the team, which is focusing on air quality modeling, and I have a background in atmospheric science. We do a lot of short and long-term forecasting of air quality. The main focus is to understand how can we design efficient mitigation measures, and we're looking at air quality policies, but of course also the link with climate change. So, working with a French Policy Support Institute, I'm largely involved in this science to policy dialogue. I've been working in the past for the United Nations, but what I will present you today is really related to my involvement in the Copernicus Atmosphere Monitoring Service of the European Commission. So just a word on expectations in relation to air quality in the European regulatory framework. We have some main items for which the European directives are designed. And incidentally, you will see that Copernicus provides a number of services which are relevant for several of these points. So the first one is member states are required to implement an air quality monitoring strategy, which includes both the measurements of air pollution, but also modeling and their forecasts. The member states are also required to assess air quality levels, in particular to know which areas are above or below the limit and the target values. And there is a duty also to inform the public about the status on a daily basis. Besides that, there are two last points which are more related to the understanding on air pollution drivers, to understand which are the main sources of air pollution episodes, and for instance, to know whether there are transboundary contributions or natural contributions. And last point, which is really important, is that member states are required to implement short-term and long-term action plans to ensure that in the future we reach the objective we set ourselves in terms of air quality. So the last 2 points are particularly relevant to the Copernicus Atmosphere Monitoring Service in relation to policy supports, and I will explain you a bit more in a minute. So this policy service is really devoted, designed through a one-stop shop website whose address is policy.atmosphere.copernicus.eu. And that website will give you access to everyday air quality forecast accompanied with advanced diagnostics. You will also be able to download elaborated reports, and through the website, we also animate a community of users for which we organize annual physical workshops. So the service is operated for the European Center on Medium Range Weather Forecast. It's actually coordinated by INERIS and involving also a number of subcontractors, which are Met Norway, NILU also in Norway, and TNO in the Netherlands. So just in a snapshot, the type of products we propose. So there is this annual air quality assessment report. These reports rely on what we call the air quality reanalysis, which were a bit mentioned by the previous speakers today. These reanalyses are an optimum between the models, which are operated at 10-kilometer resolution over Europe, and observations, which can come from the in-situ network or satellite data. We do this fusion, and therefore we can deliver on the Atmosphere Data Store a number of maps for the long list of air pollutants, which are listed on the slides, as well as pollen species. So on the basis of that reanalysis data, the Policy Support Service comes up with these comprehensive reports, which are published on an annual basis. It's what we call this interim and the annual assessment report when the data is fully validated. And they are accompanied also with dedicated reports that are devoted to the evaluation and quality control. We had a few questions before on the reliability of the data, and these quality assurance, quality control activities are really instrumental. Besides the report, we provide access to the numerical data, interactive tools that are accessible on the website. So this is for the annual view, the long-term view. And then if you focus on the day-to-day air quality forecast, you can look also at shorter case studies report, where 3 to 5 times a year we publish dedicated activities, and also interactive tools, which I will present in a minute. Last point on documentation is just to provide you a reference on our catalog of offer to actually make the best use of the Copernicus tools on the website. Just a word on the methods. So we're using really a lot modeled information for the assessment of air quality. So CAMS mobilizes an array of different models. They can be at the global scale. It's the model which is called IFS Compo. It runs at about 40 kilometer resolution, but covering the whole globe. And over Europe, we have an ensemble of models which are operated at the moment at 10 kilometer resolution. These models are supplemented with this reanalysis, the data fusion assimilation part, but also machine learning post-processing to optimize the forecast. And then we have a different suite of models which we use for source apportionment to actually understand the drivers and understand air quality. And here we have different methods that can be used. You can either do an experiment when you remove a source, so model sensitivity experiment, or you can try to tag the sources in the model to assess, for example, in this little schematics, to assess what is the importance of domestic heating in the overall air quality. So it's just to explain you a bit the methods, but now I want to be more concrete and showing you precisely what it looks like. This is a typical forecast which you can access on the website when you go to the daily product and try to find the chemical specification. Took an example which was for the city of Malaga in southern of Spain on forecast day, which was in February, 20th of February 2023. When you click on that date and that receptor, you have the 3-day forecast, which is shown in front of you, and you will see that there is a strong buildup of PM10, particulate matter pollution, which is actually due to dust. It's showing that there is a strong influence of Saharan dust being transported towards Europe and being responsible of the PM buildup for that day. If I take another example, just a week before in Paris, and here we had quite a couple of days with high PM loads, and then a clear improvement at the end of the period. And here we look at the chemical specification, again, the PM species, and we realize that it's the species called primary organic matter, which is responsible for the buildup of air pollution. What's important for the practitioners is to know whether these sources are due from local places or transboundary air pollution. And if you go to another viewer, which gives you the potential impact of the various neighboring countries, you will realize that for that day, there are very small contributions of the neighboring countries on air pollution in Paris. And actually, the largest part is due either from sources in Paris itself or from the rest of France. So really, there is a potential for mitigating air pollution at the scale of Paris and at the scale of France to reduce air pollution for this particular episode. Now you can also look at different views, which are not day by day, but on yearly views, to actually have a glimpse of the various contributions. So here it's an example for Brussels in the year 2024, where you will see which are the main countries that contribute to PM air pollution in Brussels over the year. And you have also similar views looking at sector apportionment. So here it's an example for Paris in 24, where you will see the main sources. Typically, residential heating is an important source in the winter, so at the beginning and the end of the year. During the springtime, we have clearly a contribution of agricultural sources. And in the summer, PM levels are lower, and actually a big part of that contribution is due to natural sources, even in Paris. Now I want to move to different air pollutants. I talked a lot about PM, particulate matter. Now I want to talk about gaseous species. Nitrogen dioxide is typically what we call a short-lived air pollutant. So when you look at the animation, this is a model, but it's actually mimicking what you would see from the satellite view, where you have clearly a connection between the source anthropogenized, very highly anthropogenic areas and the nitrogen dioxide plumes. If you go to a different air pollutant, which is ozone, the picture is totally different. ozone is typically what we call a long-range air pollutant. And you will see that it's building up every day. And typically, if you look at the northeastern US, you have the daily buildup of ozone. And what is important is you realize that once ozone is formed, it can be transported over very long distances. And basically, this example of the Northeast US, you will see that the plumes are transported all over the Northern Atlantic Ocean up to reaching the European area. So it's typical a long-range air pollutant, which is a bit more complex to grasp than PM because of this non-linear chemistry responsible for the formation of ozone. But we designed specific tools to understand ozone air pollution in the Copernicus Atmosphere Policy Service. This is an example of an emulator, which we call the Air Control Toolbox, showing you a summertime episode, the 10th of July 2023. And with this emulator, we can actually explore what would happen if we were to reduce air pollutant precursor emission. So here we're playing with two scenarios, one where we cut 50% of the emissions related to road transport. And on the right-hand side, we cut 50% of the emission related to maritime shipping. And actually, on both cases, you will see that over a big part of Europe, we managed to reduce ozone air pollution. So we have the blue colors when we reduce ozone as a result of these interventions. But there are areas where we actually increase ozone because of this nonlinear chemistry. Sometimes when you reduce emission, you increase ozone. It's particularly the case when you cut road transport emission over the Netherlands, not so visible, but there are some small red spots. But the red spots are really visible when you cut shipping emissions, again, offshore of the Northern Sea, but also in the Mediterranean, really close to the source areas in the maritime tracts, which are above North Africa. So this is also seen when you look at the day-to-day forecast. Another example, but still Amsterdam, so Netherlands, July 2022. And you have the day-to-day ozone, which is the solid line, and the various stacked bars are inferring the relative contribution of activity sectors. There is a big natural contribution for ozone. But actually, if you look on the worst day, when you really have the ozone peak, it's actually that buildup is due to the anthropogenic sources related to industry and traffic. So that's on the 19th of July. If you go on the previous day, actually, it's the opposite, and traffic is leading to a reduction of ozone. So it's really important to change each day the strategy you have to improve air quality because of this nonlinear chemistry. So I'm finished, and I just want to conclude with these words, highlighting the fact that the Copernicus Atmosphere Monitoring Service now offers a wide array of information that are relevant for air quality practitioners. It's very important that we can rely on this full, free, open, transparent, and quality assured information. We have day-to-day forecasts. We also have long-term reanalysis, and we know that those are widely used for downstream applications. And for the policy users, we also design some more advanced diagnostics that address specifically their needs in order for them to better understand how to target mitigation measures, how to target the sources which are the most important to improve air pollution, and also to provide air quality practitioners the required information for them to implement the regulation under the European directive and address the expectations of the regulation. With that, I'm finished, and I'm happy to take any questions if you have.
Thanks a lot, Augustin, for your presentation. It was really interesting and nice to see something like that. So, and we have a few questions for you, obviously. Okay, so the first question, how do you measure annual NO2 concentration? Are there any tools or devices you use to collect the data before including it in your air quality report?
So most of what I've been showing today was based on models or models fused with observations. So as far as the observation that we get from the field are concerned, we can get them from various sources. I think the main one in the products we use today are issued from reference air quality stations that are operated by a number of networks in the field in Europe. Basically, if you look at Europe, today we have thousands of stations that are reporting on a near real-time basis and we have free open access to all this data. Besides the regulatory data, we also use a lot satellite information, and now also more and more low-cost sensors. The low-cost sensors are not really used in the product I've been showing today, but the satellite data are instrumental, especially for the Copernicus service, which deploys a number of satellite observations. NO2 is a very good product, especially in relation with the Sentinel-5P satellite and the Tropomi instruments. And very soon, basically this summer, we will have a new satellite which will provide geostationary information for NO2. So that's also a very important source of information. And we rely on these observations as well as models to provide the best estimate in the reanalysis data that I've been showing.
Okay, thanks a lot for the explanation. I guess it's answered the next question, which is how accurate are the results for the simulator and what statistical methods can be used to reduce ozone air pollution. So it answered at least the first part of the question, more or less.
Yes, so you can, I mean, we do a lot of quality control. Chris Stewart in his presentation also mentioned the fact that if you go to the CAMS website, you have access to all the quality control information where we compute every day the statistical indicator that gives you confidence in the quality of the product. And then there is this question about the simulator. So the simulator, if I understand well the question, is really the app, the emulator app, where we are mimicking what would happen if you reduce by 50% this or that activity sector. So in the way we do that is we operate models, and we actually, in the model, you do a numerical experiment, very much like if you were playing with a digital twin. You have a model of the Earth, you have a model of the European atmosphere, and you play an artificial experiment where you say, what if we cut road transport emission? So to make sure this works, we have designed the model and we have designed the emulator. We have a scientific paper, it's referenced on the website, which show that the emulator reproduces the full model with an accuracy of 1 to 2%. So that's the trust we have in the model. But the actual experiment itself cannot be tested because we never do in real life an experiment where we reduce half of the emission of the road transport and to see if it works. Actually, we did it once, we all did it once for the COVID-related lockdown activities, and that's a very relevant experiment for us to test the models. But to actually experiment with the other sectors, it's very difficult to validate the approach. So the next question is about the access to the air control toolbox, and it's again on the policy website. So if you go policy.atmosphere.copernicus.eu and you scroll down and look for the air control toolbox, you will be able to play with the emulator.
Yeah, we put the link on the chat for the participants. So yeah, don't hesitate to have a look and go over the page. Thanks. Okay. Does all models use the same strategy for output production, given their variety in resolution and approaches for chemical composition?
That's a good question. So basically, the European Forecasting Service is relying on 11 models. These 11 models are very different, and that's the very point of having an ensemble. We want to have different models, otherwise there's no point to have 11 of them. But there is a quite stringent, very stringent common production when we actually define the terms under which condition the model must be operated, and in particular, which type of output species they must deliver. So all this is streamlined and coordinated to have something consistent in the production, which we can analyze, and the users can also make use of.
Okay, thanks a lot. So the next question, actually, we have two kind of the same question. Is it available for the whole globe, or is it only on 40-kilometer resolution for European France? And also, does the services cover other countries outside Europe, like Egypt, Africa, for example?
So the policy service I just mentioned is only covering Europe. But there is this global forecast, and that's the global forecast which is operated at 40 kilometers. But that forecast is only giving the state of air quality, and you can access the best maps for very many different chemical species. But the advanced diagnostics, when you can play with the scenarios and look at this source apportionment of air pollution, is really focusing on Europe.
Thanks a lot. And yeah, concerning the other question about the services, if it's the Copernicus services in general, you can find data all around the globe. But yeah, for this type, it's only focused on Europe. Okay, so the next question, thank you for the presentation. So can we export the results as PDF or Excel tables?
So, and I can also answer the next question. The results are available actually on the website. When you access the website, you can download the results as a JSON files. So you have the numerical data, and that's the format we provide. So you can actually then bring these JSON files into Excel or any other processing tools you may want to use. And actually, we also designed some Jupyter notebooks to help you get a bit more familiar with the data. And I noted again in the presentation of Chris Stewart that there was a link, a GitHub link towards the notebooks that are designed in the Copernicus Atmosphere Monitoring Service. And I encourage you to go back. So it was in the last slide of Chris, and you can access to these notebooks, which and one of them includes the use of the policy service products.
Okay. Thanks a lot. So, yeah, and yeah, the slides will be made available today, so no worries, along with the recording also. Okay, I think we have time for this question also. What coding skills are needed to utilize the resource at hand? Do we have to process particular coding skills?
So if you want to use the notebooks, I mean, it's relatively straightforward, but still you require some coding skill. But the viewers, what I've been showing you in my screenshots today is really an interactive website, which we designed for policy users. The policy user is not really a politicians, but in our stakeholders are actually the people working in the ministry or working in environmental protection agencies, and designing the policy support for politicians to make decisions. And these people working in environmental protection agencies, some of them have some computing skill, but they are not scientists or academic people. So it's also why we designed this more intuitive viewers. And many use we are aware of in Europe are people using the interactive tools, making screenshots to support the reporting they do at national scale. So, of course, you can have very sophisticated coding skills. You can go to an advanced use of the service, but if you don't, you can also directly go to the website and get the information you're looking after.
Okay, thanks a lot for the explanation. Okay, so that's it for the question for today. Thanks a lot, Augustin, for your presentation. We have a few unanswered questions that I will send you later on. But yeah, so thanks again for your participation and joining us today.
Thank you.
And yeah, so now we will go to the next use case, so which is André. Welcome, André.
Thank you, Gael.
And yeah, you
Very
can
nice.
start for.
Perfect. Thank you so much. Very nice to be here today. My name is André Brodtkorb. I'm a professor of scientific computing, which means that I work with both mathematics and computers, sort of the intersection there. I'm also the head of the Department of Computer Science at Oslo Metropolitan University. And today I'll be showing you some volcanic eruptions and how we can try to estimate these. Not going to today, but kind of going tomorrow, making the predictions on where the ash is going. And you may ask, why is this really a relevant question? You don't hear too much about volcanoes on a day-to-day basis, but these are huge events when they happen. So back in 2010, we had the Eyjafjallajökull eruption at Iceland. And if you look at this image here, you can see the small farm, which is here in the scenery. You can see sort of the extent of the height of this ash plume. Now, the thing that happened was that the complete European airspace just shut down completely. And that's terrible if you're on vacation, because suddenly you're stuck on Schiphol with thousands of other people not able to go home. But that's a minor issue. It's much worse for the people who need ambulance planes and helicopters and other assistance, putting out fires with airplanes and so on. So a lot of important societal infrastructure depends on airline traffic. So we need to know where this ash is and where it's going. So I'm trying to give you today some idea of how we can answer the questions, how much ash is there? Because a little bit of ash might be okay, but too much, and it's a challenge for the airline engines. Because what happens is that the volcanic ash turns to glass in the jet turbines, and then the jet turbines cease to work. And then you have a huge problem if you're in an aircraft. So you need to know how much it is, which latitude, longitude, and what altitude. Could you fly above the ash cloud or below? And also at what time? When is it safe to fly at what point? Now, the thing that we use to do this, and this is, I'd like to mention that this is a collaboration with the Norwegian Institute of Air Research and the Norwegian Meteorological Office. So we've done this. We look at the weather forecast. And if we know the weather forecast, we know where the wind is blowing, and we can estimate where things will drift if we know where they are today. And then if we know what the exact volcanic eruption was, we can predict the future. So here you see an example. Let's say we have 0.2 tons of volcanic ash at 1,000 meters of altitude. And then we have 2.5 tons of volcanic ash at 3,000 meters altitude, and then 4.7 tons at 5,000 meters. Then we can advect that with the weather forecast and give predictions to the airlines and the relevant public actors. But it's not so simple. We need to figure out how much ash there is, because we don't know that. We could start with like an uneducated guess, having an expert thinking of a number. The problem is that we don't really have these experts readily at hand when there isn't an eruption. But then we could make more of an educated guess. We could find a similar historic eruption. We could look at on-ground deposited ash, measure the ash cloud height through these planes or radar. Or we could do ground concentrations of ash through air filters. But all of these have a time delay before you actually get it. What we can do with the satellite images is to see the whole extent of the ash cloud as visible from a satellite, which is really valuable. Now, we've been using the Slister instrument from Sentinel-3, and this instrument can more or less capture the temperature. So think of this as an advanced temperature sensor, and it gives you the view of the Earth's temperature. The very cool thing about this satellite is that it has two directions where it can view things. It can view through the nadir swath, that's the perpendicular swath down here, about 1,400 kilometers. And then it has the oblique swath. So when the satellite setup flies above the Earth, it will capture the same exact point on the Earth from two views. And that gives us a stereo view of a potential ash cloud. And we can, from that, deduce the altitude. So we can see if it's 3 kilometers or 7 kilometers or so on. And that's a really good benefit to increase the precision of our estimates. But this is difficult. It's really, really difficult because what we're trying to figure out is what was emitted at the volcano originally up here that could cause what we observe with the satellite many hours later on, because the ash which has drifted on takes a lot of time before it moves on. So this is the challenge. How can we figure out the eruption that could explain what we see in the satellite's images? So in come mathematics, a very good tool that I love. And I'm not going to show you any formulas today because they're a bit too complex to grasp in 15 minutes, but I'll give you the essence. In this graphic, we have two important things. It's the satellite images. They will give us an estimate of how much ash we think we observe, and I'll come back to why we think we observe it. And then we have some potential emissions. So this unit emission simulations, those are potential eruptions. And we want to find a combination of these potential eruptions that could explain the satellite observations we have. In addition to these two input parameters, we have an initial guess, sort of to guide our mathematics into finding something which is physically plausible. Because in this mathematical framework, it could potentially say that, well, if you admit minus 1 ton of ash, like negative amount of ash, you could explain the satellite observations. We know this is not physically plausible, so we sort of need to limit it at some point. But if we take these three inputs here, the initial guess, the satellite observations, and all of our potential eruptions, gather them into a huge mathematical matrix, we can massage this matrix using some mathematics and come up with a better prediction of what was actually emitted. And you see, in this case, we go from an initial guess with quite a large eruption on the 14th of April around noon to something which is reduced in magnitude in terms of how much ash is emitted, but the concentration is much higher and it's much closer to ground. So here, the inversion framework helps us to say that the actual layer in which the significant ash was erupted is closer to ground than what we originally thought. All right, the unit emissions. These are potential eruptions. Now, to make the mathematics work better, we systematize it a bit. So first, we pick a time point. Let's say the 16th of April at noon. And then we run different scenarios. In scenario 1, we emit 1 ton of volcanic ash, 1,000 meters above ground. And that will give us an ash cloud which looks like this a couple of days later. If we do the exact same experiment, but emit the ash at 3,000 meters altitude, we will get a different scenario. So you see the ash cloud has actually moved into different places because the wind is different at 1,000 and 3,000 meters above ground. And the same, of course, with 5,000 meters. So we do this. We advect volcanic ash emitted at different time points and different altitudes to generate a huge set of different volcanic eruptions. So it's a quite complex thing to imagine, but think of this, a whole set of different possible volcanic eruptions. And that's the one input we use. The other input that we use are the satellite images. And unfortunately, even though we have very good instruments, nature is not always playing nicely. So this is not as nice a photo that I showed earlier, where you see that there's a mix between the volcanic ash, which is this darker brown cloud, and the lighter clouds, which are regular clouds. Now we want to detect sort of a temperature difference here and say that, well, we think that this brown cloud here is volcanic ash. The problem is that up in the left-hand corner here, for example, this is not volcanic ash. But according to the instrument, it has a signature which looks a lot like volcanic ash. So we do get some so-called false positives, which tell us that there may be volcanic ash there in terms of our measurements. But if we look at like the image here, we see that this cannot be. And so you see also there are other places here with these green to yellow colors, which show that there may be some ash here in which we know that there is no ash. There are other things in this image. The blue ones, they show that here we know that there is zero ash. And then the white one is we don't really know. It's difficult, for example, this cloud system up here, to say whether it's ash or volcanic ash, whether it's clouds or volcanic ash. And then finally, we have some things down here where we may have some false negatives. If we look at this image, we can see that there must be an ash cloud here because we know there's an ash cloud which has reached the coast of Norway. There should be some ash here, but it may be beneath some clouds which are higher in altitude. So from our satellite, it looks as though there's zero ash here. So we do have these issues that we have to work with in the mathematics. So it's not as simple as just having the mathematical tools and then getting a perfect solution. We have to work with a lot of uncertainties. Now let me show you a video. This is a video of the eruption as viewed from the satellite. Now you can see the timing, it starts on 13th of April, so the big eruption comes a bit later. But look at that when you see this movie, you see that there will be no ash in the beginning. And that's because it's covered by other clouds. So yeah, now it's running. You see that there may be some traces of things that we think may be volcanic ash. You see some, maybe some false negatives here and there. And then at some point, we see the second eruption period, where you see that, well, here we have some proper eruption going on, which we can model and see that it actually runs through. Okay, so that was more or less the volcanic ash detections. And you see that after at some point, it becomes difficult because there's a lot of volcanic ash in the atmosphere, just residual, just working its way around these low and high pressures. Now, I started with the saying that we had these inputs, the unit simulations or the potential volcanic eruptions, and then we had the satellite images, which give us the observations. We gather these into a so-called source receptor matrix, which tries to correlate them to say that, well, if this eruption looks a lot like what we observe, we give it a higher weight. So we end up with this kind of matrix, and this matrix is huge. So if you look at it here, this has something like 600, 700,000 lines or rows in it. It has 1,200 or so columns. So there's a huge number of measurements and simulations that we try to correlate here. By doing this and massaging this matrix, we get something like this. Now, I want to just quickly explain to you what you were looking at here. On the right-hand side, we see the exact same we saw earlier. These are the satellite images, just the observations. And the bottom here, which is this panel here, shows our initial guess of how violent the eruption is. So it starts off with quite a significant eruption, a second eruption here, and then a third big event over here. On the left-hand side, we're going to see our simulated results. Now, the really important thing that I want to highlight here as well is that going from these satellite images to something that you can use in an airplane or in an air traffic controller setting, you need more information. So look at the difference between the scarcity or the sparsity in the satellite images and how much we kind of fill in on the left-hand side. Finally, you're going to see three different colors. It's going to be red, it's going to be gray, and it's going to be turquoise. And these three colors correspond to the different levels of ash which are used operationally when forecasting ash to airline pilots. So here we go. You see on the left-hand side, it's a much more detailed photo or image of where the volcanic ash and potentially is, whilst on the right-hand side, you barely see anything. You have no idea where it is. And especially when it comes to the concentrations. And then we come into the second larger eruption period, and you see that the inversion here comes up with quite good descriptions of the eruption once more. And finally, we're nearing towards the end of this kind of major, or yes, major volcanic event. And we see that the ash cloud also just disappears. Good. Then I want to end with a short summary. It's really important to forecast these volcanic ash clouds when there's a volcanic eruption. But it's difficult, and it really needs these satellite observations. But it also needs the forecasting capabilities to make sure that we get a more detailed view than just what the satellites can give. And the cool thing about this work is that it appears somewhat robust in terms of what results it can give compared to just having a best guess from an expert. So with that, I'd like to thank you for your attention, and I'm open for questions.
Thanks again for your presentation, André. It was really nice, and people enjoyed the little animation at the end. So thanks for that. So we'll go to the question, and the first one being, what is the function of the sea and land surface temperature radiometer mentioned in the presentation?
Good question. It's difficult to detect volcanic ash. So the slister or the sea and land surface temperature radiometer will give a slight indication that the temperature signal from volcanic ash is different than regular clouds. So you can distinguish between regular clouds and volcanic ash. And by doing that, you can identify where you have ash, which then comes as the input to the mathematical framework.
Okay, thanks a lot for the explanation. It's clear. The next question being, which satellite data was used for the modeling?
So I think this exact one, I believe, was from the Slister instruments. So this is back in 2010 satellite imagery, which goes back then. But it's the details are in the paper, and the cool thing here is that the exact data which are used to produce these results are also on Zenodo, so you can download it all and run it on your own computer. And that's one thing that was kind of missing from this presentation, but one of the aims of making this framework was also to make something which is fast. Previously, this had to be run on a supercomputer with about 200 gigabytes of memory to be able to run at all. We reworked this so it runs faster, and now it runs on a regular laptop. So you can run this on your laptop computer.
Okay,
So,
okay,
yeah.
then. Okay, thanks a lot. So, and yeah, the paper was made available on the chat, so people can also have a look at that. Okay. Next question, when measuring a volcanic ash eruption, what other factors are typically assessed during the eruption?
Well, there are so many volcanic, I'm not a volcanologist, so I don't know the details, right? But there are so many things. Like you don't necessarily care about how much ash is erupted, you care about how much ash remains in the atmosphere. So you want to know the fine ash fraction and these things. So detailing what happens during a volcanic eruption goes a bit beyond my expertise, but it's a lot. And it's also sometimes other gases that don't turn up on satellite images that you really care about, which you only can pick up with ground sensors, like sulfur and these things.
Okay, okay, thanks a lot. Okay. How can your model be cross-checked with in-situ data?
Good question. How can we cross-check this with reality and make sure that we actually model something which is real and not just a fantasy? Satellite images are somewhat of satellite images give us some indication. It's difficult because what you get on ground is the fallout of the volcanic eruption. So you're not necessarily the thing that you care about. So it's difficult. You do have some volcanic eruptions where you have planes which fly through the ash cloud, and you can actually get some concentrations here and there, and those may be good. So the cross-checking here is like a qualitative assessment compared with other results of the same eruption, because this is a kind of well-studied volcanic eruption up towards the measurements that we have.
Okay, thanks a lot. This question, so does the example Jupyter notebook that has been used for this example is available to demonstrate the best use of satellite observation?
Well, I think the actual Jupyter notebook that was used to make this video is on my personal computer, but I have no problem making that available. But everything else, like making all the data available, that's just open and on Zenodo, so it's available for eternity in principle. So if there's requests to get access to it, I'd be happy to share it. There's no, yeah.
Okay, thanks a lot. I think your contact is on the slides, if I'm not mistaken, so people will be able to contact you. Thanks again. Okay, this is kind of an open question. Can we make simulation by using the same concepts to simulate an explosion of a nuclear plant? Sorry.
Yes. So there has been this exact framework has been used also to study part of the Chernobyl incidents. So this same mathematical framework can be used, but there are differences in how the atmospheric chemistry of radioisotopes and volcanic ash are different. So you need to have different mathematical tools there. but it's possible. So the inversion procedure is definitely possible to use there. But a challenge with nuclear power plants is that you have fewer observations. With satellite images, you can see the whole area you're interested in, but with radioactive isotopes, you basically just have point measurements. And if your volcanic or if your radioactive ash cloud is just a kilometer away from your point source, you will get 0 on your point source. So it's a challenge with the observations.
Yeah. Okay, yeah, thanks. Good to know if you people want to try, but yeah. Okay. Okay, next question. Can this model be used for predicting other volcanoes in Asia or the Pacific?
Yes. So if you have this requires that you have a way of advecting the ash. So as long as you have a way of simulating the ash going forward, you can use this framework. So I don't have a setup for predicting volcanoes in Southeast Asia or the Pacific. So, but if you have that, the source code is there, and it should be relatively straightforward to actually plug in the different sources and make this run.
Okay, thanks a lot. Okay. Did you use inversion modeling here or machine learning? What is the name of this model or machine learning used here?
Yeah. So this is where the magic sauce is hidden, right? Where you're actually doing. This is not machine learning. It's a traditional inversion, so it's based on least squares inversion. The formulation, sort of when you formulate your least squares, it has to be in some sort of basis, and the basis here is important. So it's formulated in special basis, and then you have to have the relaxation parameters to make it give physical answers, because there's nothing in least squares to make sure that it's physical. So it's essentially least squares with some add-ons to make it sure it's physical, robust and physical. Yeah.
Okay, thanks a lot for this answer. We will have time for 2 more questions. What workflow orchestrator do you use, and what supercomputing service do you employ?
Okay, so I don't know what workflow orchestrator means in this context. I'm going to interpret that it means like the batch scheduler for the supercomputer. I think this was run with Slurm on the Nordic Cooperative Operational Infrastructure for Metrology. So this runs on the MetCoop infrastructure, supercomputers. This was actually run on one in Sweden. But the inversion procedure, after you've run, that's for the forward modeling, the potential volcanic eruptions. But once you have those, everything can run on your laptop.
Okay.
Yeah.
Okay, well, good to know. Also, thanks. And yes, so for the last question, a more open question, can volcanic ash contribute to climate change? If so, how?
A wonderful question. I think the definite answer is yes, it can contribute to climate change. The details of how is way beyond my knowledge, unfortunately. But I know it may have some cooling effects, but this is just from me reading things, not me as an expert.
Okay, thanks a lot. Yeah, so that's it for the question for today. So we have some unanswered question, of course. I will send them to you later on by email, and like that, for the participants, you will be able to have the answer for your question. Yeah, thanks again, André, for joining us and your nice presentation. It was really nice to have you.
Thank you, Ed.
And yeah, we will go to the last use case of the day. So a presentation by Konstantinos. And yeah, so Konstantinos, welcome. And whenever you want, you can start your presentation. Yeah, I can hear you now.
Okay, nice. Now you can hear me, right?
Yeah.
Okay, so good morning, everyone. My name is Konstantinos Politakos, and I'm a research assistant at the Remote Sensing Lab of FORTH. Today, I will talk through a project that brings together remote sensing and flux observations to evaluate airborne CO2 emissions, specifically heating emissions modeled by ECMWF and assessed through eddy covariance flux measurements in Iraq and Greece. This work was carried out as part of the WEkEO project. Now I know that many of you are experts in remote sensing, but eddy covariance might be a new territory. So essentially, the goal was to build and test prototype systems of the CO2 MVS that will operate under Copernicus. What made this project powerful was scale and collaboration. As you can see on the right, there were many research infrastructure, laboratories, and universities that actually collaborate within this project. Together, the project delivered tools to estimate emission from global to city level. Now we'll see a few key objectives of the project. First was to deliver prototype systems for estimating anthropogenic CO2 emissions, like the mandate that we will talk later on. Second, to engage this with users, with scientists, policymakers, and service providers to make sure that the systems being developed are actually fit for purpose. The third one, the understanding and quantifying the uncertainties. And fourth, the system provide early inputs to first global goal state. And finally, to support the operational implementation of this system. So now some key deliverables through this project. As you can see, here's a concept figure showing how we can split the overall process of satellite-based CO2 monitoring into components. Here we have deliverable 5.5, showing how sensitive the model outputs were, particularly for road transport emissions, to different assumptions, and as well as the total CO2 emissions from the WEkEO inventory on the left, and on the right, the standard deviation on those estimates when the input parameters were perturbed. Also, we have the collaboration with AGH University of Krakow, where we had they delivered measurements through tethered balloons and drones in order to have vertical observations of crucial GHG concentrations like CO2 and methane in order to help and support the inversion modeling. Now we'll take with me the point 5 in order to talk a bit about the WEkEO. So what it makes this powerful is that the satellite and model-based information is integrated in one place and make it easier to combine data sets and support downstream services. Within this was also the WEkEO project, which was built on the wealth of the Copernicus data. Here in Iraq and FORTH, we also had the ERC Synergy Grant, Fair, which also focused on understanding the feedback between urban transformation and climate change. And last but not least, we recently have joined we are leading the CLMS SEEDS program, which is the extent of Copernicus land monitoring service into urban applications, especially those involving greenhouse gas inventories and city smart planning. So now, the two deliverables that we used, our flagship observation was deliverable 7.10, using both flux measurements and modeling approaches, which include the eddy covariance data and flux footprint modeling that I will talk later on specifically, and the composition into source components like traffic, heating emissions, and vegetations. And on the right, the deliverable that I will talk today is deliverable 3.2. Which include the models like MENDI and how to better align models with ground-based observations. So now let's see how the model of ECMWF MENDI actually worked. Through task 3.2, a residential CO2 emission model that operates within the IFS, the Integrated Forecasting System, and focused specifically on heating emissions from in situ fuel combustion. Three main recommendations of this model was the use of the model within an urban sim. We'll see this later, specifically for Iranian case study. The extending of the monitoring network That's why we used our eddy-covariant flux towers along the study. And the third point that I will not focus on this speech is the use of point source emissions directly on the IFS grid. So what was actually delivered by mainly was the implementation of an urban canopy model, which perfectly aligned with Heraklion city, and then later was implemented through the IFS camps and the IFS Menti model in order to get a final CO2 heating map, CO2 heating emissions map. As you can see, in the middle is concentrates the buildings and the residences of Heraklion. That's why we see higher heating emissions through the city center. And how did this model actually work? Meant start from nationally reported annual residential emissions, and then spatially and temporally disaggregates them based on urban land cover and soil temperature. Around 20% of emissions are assumed constant, and the remaining 80% are linked to space heating demand, which is modeled using topsoil temperature. The threshold for the heating these days was set up to 15.5. So now we'll just talk about how we use flux observations within an urban landscape. This is the equation that actually we use when we're talking about the urban flux measurements. VFC is the total net CO2 flux that we meet in a city, and it consists of emission from traffic, which consists of buses, trucks, or vehicles. Also, some building emissions, which consists of heating emissions from fuel combustion. And of course, the human metabolic CO2 release, the soil respiration, the plant respiration, and the only term which actually has a minus sign is the photosynthetic CO2 uptake. It actually absorbs the CO2 from the atmosphere. So now we have here the Heraklion case study. If you follow the red line, you start from Greece, you go to Crete, and then to Heraklion. Here in Heraklion, we operate two flux towers, HEKOR and HEKMAS. The one on top is HEKOR and operates from 2A16, the city center of Heraklion, and HEKMAS, a second one in the residential area of Mastabas in Heraklion. What's important to mention here is these colorful areas. So you see a detailed satellite view of the city with modeled flux footprints, which I'm going to analyze later. These show the dominant source areas from each tower under prevailing wind conditions. These two flux footprint areas come through annual datasets, so we can see that we have a strong influence from the northern and the southern parts of the location of each tower. So I'm gonna grab the HEKOR images, and I'll just continue on the eddy covariance method and how it's used through the urban landscape. Eddy covariance is the only direct measurement technique that captures the vertical exchange of heated mass like CO2 between Earth's surface and atmosphere. You see here that the instruments are actually placed within the inertial sublayer and not in the roughness one. That's why the roughness sublayer is influenced by individual building and trees, while the inertial sublayer above that is where we can measure fluxes that represent the aggregate signal from the surface. So that brings us to the concept of the flux footprint, the upwind area that contributes most to the measured flux. The extent and the shape of the footprint varies from wind speed, wind direction, and surface roughness, which help to determine which is the key to identifying and interpreting different emission sources. like heating, traffic, or human respiration. However, interpreting all these sources is really difficult through the complex urban areas. So on the left images, you can see on the top, the sensor is mounted above the urban surface. The source area is in the perfect cycle. It's shaped by wind direction and turbulence. And on the bottom, we see the footprint stresses in the downwind direction depending on atmospheric stability. Understanding this is really crucial. That's why I have to mention all this methodology, because it tells us what part of the urban surface we're comparing with the model, with the Menti model, and how will this grid cell align with the flux footprint. So here is once again the image of the HECOR as it's operational till today. You see on the bottom right image that this is a 17 meters high building, and of the roof of the building we have established a 10-meter mast, and at the top of the mast there is the irrigation, the gas analyzer that measures the CO2 fluxes. Okay, now, on the left, we see high resolution land cover classification over Iraqian, including building roads, vegetation, and bare surfaces. This work based on a recent published paper by Savsagakis by 2019. The white contour lines represent the model source area of the tower for a year. This is why I told you before that this is annual measurements, and this shows the high influence that we have from northern and southern direction winds. And if we take a closer look to let's say to a 30-minute measurements, we see that. Can you hear me?
I think we lost you for a few seconds. And your picture is still frozen, but I can hear you.
Now I cannot see the screen. I cannot see anything.
Maybe you can try to leave and reconnect, perhaps. I don't know. Sorry for the short break. I think we will tell Konstantinos to try to come back in a few seconds. Maybe, probably a connection issue. Okay, so yeah, so sorry for the delay for the participants. I think Konstantinos managed to quit the Zoom meeting. He will probably be back in 1 or 2 minutes, so stay put. Are you again, Konstantinos? Can you hear me?
Yeah, I can hear you. Yep.
Yeah, okay. So maybe if it's a connection issue.
No, I think that something went wrong with the Zoom platform.
Oh, okay.
Yep.
But we can hear you now.
Yeah, okay, I will continue. So on the left, we see a high resolution land cover classification over Heraklion, including building roads, vegetation, and bare surfaces. This is based on work by Stavros Agakis at 2019. The wind control lines represent the model source area of the tower for a year, and the footprint that contributes most to the flux signal. That's why I would like to focus. I cannot control the on a 30-minute measurement, which actually is strongly influenced by only northern winds. So when we get an annual flux observation dataset, we see that we have strong influence from the northern and south part, and we know actually the main source area of our measurements. So in this project, we also have the help of and assistance of the ICOS associate flux tower from Basel. Basel is a city in Switzerland, and we use the flat footprints from this city in accordance with the model MEGDI, once again, where we can see the high influence of the heating needs from the residents throughout the year. That's really pretty normal, since the Switzerland is much northern than Heraklion, so we can see greater heating emissions throughout the year. So let's see the final evaluation of our model. Now we can return to Heraklion, this time showing how we aligned our measured CO2 fluxes with the MENDI model outputs. On the right, you see a land cover map of the city, which includes building, roads, and vegetation and water, for modeling and interpreting urban emissions. So as a quick reminder, I'd just like to say that models and observations may speak different languages. It's important to align sector, spatial coverage, and units. To make comparisons meaningful, we collaborate with ECMWF, who provided downscale MENDI output for Heraklion and Basel at 1 square kilometer resolution. And next, why we selected HEKMAS Tower in the residential district of Mastabas, and why not HEKOR? HEKOR is dominated by traffic and commercial activity. Over 7% of CO2 flux which come from traffic alone. And so also the Basel towers are also near roads and commercial areas. In contrast, HEKMAS is mainly influenced by residential heating. It's a quiet neighborhood with dense housing and modest traffic. We focused on the winter season from December 2021 to April 2022, when heating demand peaks. We compared the daily MENDI model heating emissions with eddy-covariance CO2 fluxes. So that's why you see through the evaluation that this the blue line corresponds to eddy-covariance measurements, and these peaks are the total flux through the weekdays. So we see how, the change between the resident behavior through the weekdays and through the weekend. That's why there is a dramatic decline, a significant decline through the weekends, through the Saturdays and Sundays, where the commuters do not accumulate in the center. So this validates the usefulness of HEKMAS in capturing real-world heating patterns and supports the MENDI model's effectiveness when sectorally desegregated and spatially downscaled. You see that during the winter months, December, January, February, March, and April, we have high impact due to heating emissions. And this comes with great correlation with the MEDI model through the ATD correlation. And then we end up with monthly medians to end up with a linear regression and R square of 96%. Still, we must remember that ecovariance includes more than just heating. It sees everything in the footprint, from traffic to respiration. That's why such careful site selection, footprint massing, and unit harmonization are vital. And now the last slide, just to wrap up. Okay. Urban ecovariance offers insight into CO2 emissions, but it requires careful interpretation while model alignment. With MENDI, context, and footprint modeling, we bridge this gap between observations and simulations. And while challenges remain strong seasonal correlation, we found remind us that meaningful progress is possible. Last but not least, next slide. Okay, if you want to go fast, go alone. If you want to go far, go together. I have to acknowledge Aura Lupascu, Joy McNorton, Margarita Hulga, Gian Paolo Balsamo, Mark Guevara, Hugo Denvier, Stavros Agakis, Flex, Thomas Kaminski, and Marcus Schulze for supporting me through all this research. Thank you very much. I'm sorry for this Zoom thing. I didn't know what happened. I'm here for your questions.
Thanks a lot, Konstantinos, for your presentation. So no worries about the technical issue. It's not a big deal, and it happens often. So for the question, we have a few for you. The first one being, besides the wind direction, what other technical factors do you take into account?
Yeah, that's a great question. I didn't mention a lot because talking about ecovariance, it's and within the urban landscape, it's a really huge chapter. But for starters, let's say that we also need a surface model in order to see the elevation and to see how our city is structured. We need a digital surface model. And we also need the building height in order to see the roughness that it's created upon all the materials in the roughness sublayer, as I explained earlier. So yes, you will mainly need the building heights, the vegetation, the trees heights.
Okay, thanks a lot for the explanation. We'll go to the next question. How will the CO2 project and the CO2M satellite mission improve the accuracy of global carbon emission monitoring and support climate policy decisions?
Yes, that's a really good question. I'm actually not such an expert on the on how to improve the accuracy, but there's a great context through the COCO2 website for such satellite specialized questions. I'm sorry for that.
Okay, thanks a lot. The link of the project was also put on the chat, but yeah, you can have a look. Thanks. Okay, can this model be used to detect emissions in rural areas and or the agricultural sector?
Yeah, that's a really good question. You see, you see within the urban sim that was created by the ISNWF was mainly focused on. There's also a paper that I have introduced through my presentation. For now, I'm not aware if there is something especially for rural areas, because if you can see, we actually focused on heating emissions, anthropogenic emissions for heating. So I don't know if ISNWF have implemented something new for CO2 emissions through the rural areas.
Okay, thanks. Maybe something in the future. Okay. Next question. How does atmospheric turbulence affect the accuracy of CO2 flux measurements in residential areas?
We have, if I am getting this question right, we have to distinguish the scales that we're talking about. You see, when we're using all these CO2 flux measurements, we're talking about local scale. We're talking about 50 to 60 meters above the ground. We cannot upscale these the measurement that we measure through our flux towers with the turbulence that it's going on the higher layers of atmosphere. So their local scales, they are the total CO2 fluxes within a context, a flux footprint area 1 by 1 kilometer. So there's no high influence from the higher scales of the higher levels of atmosphere. But if you talk mainly for urban scale and below the 60 meters, you may understand that there are skyscrapers, there are all these buildings, there are the trees that actually interfere and affect the turbulence and how the CO2 flux are measured within the urban setting.
Okay, thanks. And yeah, it's kind of the same question next about how can machine learning and modeling can improve.
Yeah, you see, there are two main contexts. The first one that we are also working here, it's the gap filling. You see, there are a lot of maintenances, there are some bad values, there are so many signal strengths that we use in diagnostics, so we may miss some measurements. There, the machine learning can actually gap fill a lot of missing values. And except for that, what we can see is that in some cases we can forecast the CO2 flux observations using machine learning, since we have a similar wind conditions and similar traffic emissions, building emissions. So we can forecast, we can foresee what we actually waiting to see from our measurements.
Okay, thanks a lot. And now we will go to the last question for you for today. How does the Copernicus CO2 project leverage satellite data and modeling to enhance the verification of anthropogenic CO2 emissions?
From this deliverable, you see that within the work package 7 of this project, we had this deliverable made by the flux towers that we have here in Heraklion, so we could implement our flux measurements, these local scale measurements with IFS, which is a global model, first of all. And second of all, we had the measurement from Krakow, from AGH University, which I talked at the beginning of my speech, where when you're measuring the vertical profile of CO2 and methane, you can better understand how to use them as validation to your inversion modeling.
Okay, thanks a lot for the nice explanation. It was really clear. So that's it for your question. Thanks again for coming.
I'm sorry about that.
No worries, it's fine. You managed to come back, so that's fine. Yeah, well, so thanks again for coming and for the presentation. And yes, so we are reaching the end of today's session. So I hope you participants enjoyed it. Thanks again to all of our speakers for coming today. And before you leave, I just want to remind you that there is a section on the website next to the Q&A reserved to the poll. So we would really like to have your feedback on today and what we could provide in the future. So if you could please take 2 minutes of your time, it would be really helpful. And as you know, the practical session will be the day after tomorrow also. So if you haven't had time yet, sorry. Just a bit slow on my computer. Okay, so I will keep talking, it's fine. So yeah, as you know, the practical session will be the day after tomorrow. So if you haven't that time yet, you can check the tutorials that we made available on the website. So they are available in full. There is the code files, the documentation, the data used. There is also a video tutorial with each of these tutorials, so Jupyter, QGIS, and R. And you can download the tutorial, start to practice, and on the second day, we will have a summary presentation of these tutorials, and our experts will be there to answer the question you might have. So yeah, thanks again to all of our speakers. Have a nice day and see you in 2 days. Bye-bye.